Okay. Okay, I think we can get started now. So, um, right. So just a little bit of a housekeeping. We got so yesterday there was kind of two tasks. So basically you had to take notes from the video and then submit the practice questions. So I haven't created the submission folder yet. I'll create it tonight. Um, and then so today what we'll do is just Unit 3 review, and then next Saturday it'll be like Unit 3 test. So from 1 to 3 p.m. It'll basically go over everything that you guys covered, and yeah, I think check Google Classroom for uh like the notes if you missed any weeks or whatnot. I think the format will be just 20 straight questions, no multiple choice this time, just 20 short answer questions. It'll be, I think 10 of them will be like true and false, and then 10 will be just the regular questions we go over today, and then I think we went over some yesterday as well. So, right. So I think for your report cards, if you still haven't received the grades yet, or not grades, I think the actual copy of it, um, Dr. Seen said he's going to send it, I think, by the end of this week. So, okay. Okay. So, guess we can here. Okay. So, uh, okay, so we'll go over this question here. So it says a 45.7 kilogram boy on a swing moves in a circular arc of radius 3.8 meters. At the lowest position, the child's speed reaches 2.78 meters per second. So the question says determine the magnitude of the tension in each of the two vertical support chains. Okay, so let's recall. So there's some there's some terminology here that's kind of not new, but I don't think we talked about it. Um, so we say that like the tension denoted as big T, the support chains of the swing. Okay, so when you have like these two support chains, I guess this is where the tension uh plays the part. So you have these basically, I don't know if it's a diagram will help, but we can draw one. So you have these two support chains, and you have the wave voice swings on a circular arc radius. Okay, wait. So hold on. Oh. So you have this guy, and he's swinging on wait in a circular arc. Determine at the lowest position. Okay, so okay, so the way at the lowest point, so they're trying to find okay where the tension in this string is at the lowest point. So so we say like at the like lowest point, the tension is basically equal to the gravitational force or mg. So we say that one sec at the lowest point, force. the gravitational force mg. Okay. So in this case, we know what mg is. We know what the mass of the buoy is and gravity is, but we don't know what tension is, and I think that's what we're trying to solve for. So we say like the net force acting towards the center of the circular motion. We'll denote circular motion as capital FC, is given by, and then we'll use this this formula. So we have FC is equal to mv squared over r. Okay, so we know what in this case m is going to be equal to 45.7 kilograms. V is equal to 2.78 meters per second, and then R is equal to 3.8 meters. Okay, so yeah. Now, at the lowest point, the net force is provided by the tension, so, and that's equal to mg. So we can write that out as okay, so actually, so we have in this case the, I'll just write it out too. So at the lowest point, net for FC is provided by the tension. So what this is going to look like is so we have FC equal to tension plus mg. Okay, so now we have to basically set these two expressions equal to each other. And then when you do that, what you'll have is you can isolate for tension. So you'll have tension plus mg is equal to mv squared over r squared over r. And then now we just solve for t. So you have basically you can bring this over to the right hand side and just have t is equal to mv squared over r minus mg. And then now what you want to do is basically like plug in all the values that you saw in the first question, or in the question here, and then solve it. So I'm just going to give you guys about like 5 minutes to do that, and then we can reconvene in 5 minutes and see what the tension is. So I will, here, 1 second, let me just Okay, there. So here's all the information that you need to solve this question, and then see what we can get. Okay, so I think the solutions look pretty close. So let's see. So we got let's write tension is equal to the mass in this case is just 40, what's it, 40, 40, 45.7. So I'll just write it out here. So 45.7 times 2.78. Um, and then and that is going to be divided by 3.8 meters. So I'm going to go 3.8 here. And then all of that is going to get subtracted by your 45, like basically the mass times gravity, which is 9.8. You have 45.7 times 9.8. Okay, and then okay, so if I do this on my calculator, it's yeah, 45.7 times 2.78. So in the numerator, you should have 127 .046, and I'll keep all the decimal points just because I think rounding before your final answer is what gives a lot of students problems. So you'll divide that by 3.80, and then that's being subtracted by 45.7 times 9.8. So I got 447.86. Okay, and then 27 point divided by 3.80. So I got, wait, oh, I forgot. This was squared. So 2 point, here, one sec, that changes it because my numerator, oh, I think, okay. So in this case, you have that 45.7, okay, well, 45.7 times 2.78 squared. So 2.78 squared is 300 and, oh, wait, that's like 2.78 times. So I got 7.7284. So I guess I'll just write it out. So it's 45.7 times 7.7284. And then that is being divided by 3.80, and then you subtract it by 447.86. So right, so numerator looks like 45.7 times 7.284. So numerator looks around 353. 353.18788 or 88. And then that's divided by 3.80. Minus 480. We'll just go for 47 or 448. that's okay to round it as you get closer to the final solution. So, and you can round these numbers that like aren't being added or subtracted anymore, but the one with the division operator, I think it's best to keep all the decimal points as far as you can keep it. So final answer is approximately 92.92. So 92.92 newtons. Okay. So that's what you should have gotten for the tension. And I'll give you guys like about 5 minutes to copy it down, or then we'll go to the next question. Okay, so let's go over the next question. So, this question is good. So we have example 2. So we have a spherical meteor approaches Earth from a great distance. By what factor does the force between Earth and the meteor increase when the distance between the centers of the two bodies decreases by a factor of 3.9? Okay, so we format this. Okay, so let's see this question. So we covered yesterday the gravitational force between two objects. It's gravitational force between two objects is given by Newton's law of gravitation. And then we can write this out as we have F is equal to big G times M1, M2 all over R squared. Where we know F is the gravitational force, G is the gravitational constant, M1 and M2 are the masses of two objects, and R is the separation between the two objects. So we know, so the question asks if the distance between the centers of the two bodies decreases by a factor of 9, then the new distance, basically you call it R prime, is related to the original distance R. So in this case, so okay, so we have this basically proportionality statement. So we have R prime is equal to R over N. And then, so we consider the ratio of the two forces, it decreases by a factor of 3.9. So in that case, what we got to do is, so we got it. Okay, so now let's consider the ratio E. Okay, so what does this look like? So this will actually let me just so what we're seeing in this case is you have F prime over F, which is basically the related force over the regular force. And in this case, it's the same formula, you're just repeating it, and then you cancel out like terms. So in this case, G M1, M2 all over R over N, which is R over N squared. And this is going to be G times M1, M2 all over R squared. It's just canceling out like terms. What we're going to get left with is just the expression G m1 m2 r squared all over g m1 m2 all over r over n squared. Okay. Simplifying this, what we're going to get is r squared all over r divided by n squared. Okay, so all we have to do now in this case is just substitute n for 3.9, and then we should have our final answer. So I'll let you guys compute this. So we have r divided by 3.9 squared. Okay, and then we know what the value of r is, so I believe it was given in the question. Uh, what's the radius? I think, one sec. Radius of the Earth. Average radius of the Earth is approximately 6.123. All right, just use r to be equal to 6.3 times 10 to the 1, 2, times 10 to the 3 meter or kilometers. Yeah, that's in kilometers. Okay. Can you give that a shot, and then we'll reconvene and see what final answer we get. Okay, so r squared. Okay, yeah. So um oh wait a second. We actually didn't even need r. Sorry, you need to input. Oh, sorry. You need to input this because basically these two terms cancel out, so you have r over r squared, like r squared over r squared cancels because this whole expression is times 2, so the only thing you're really multiplying is 3.9 squared. So your final answer should just be 15.21. And just write a quick therefore statement. So we say therefore the force between Earth and the meteor increases by a factor of approximately 15.21 when the distance between okay. So 1 second, let me just say